All right, this is physics lesson 5.05, calculations with friction. This might be a part one. We'll see how long this problem takes us to do, if I want to split it into two parts or not. So we've got a 24 kilogram crate, initially at rest on a horizontal floor. It requires a 75 Newton horizontal force to set it in motion. Find the coefficient of static friction between the crate and the floor. So we've got our box, and it's setting on a surface. All right, so let's start off by listing, let's do a coordinate system, and I want you to list the forces that we need to put onto the box. And pause the video if you need to think about it. Well, in this case, we're going to need four forces. We're going to need the weight vector. We're going to need normal force. We've got an applied force, so we now have an applied force that we're talking about. And of course, these are problems that we've got frictions. We have to do four problems. But before I can start putting vectors on, I'm at rest. We need to dissect this problem a little bit. So I'm at rest, and we are just beginning to set it in motion. So what this means is two things. First of all, if you're at rest, your net force equals 0. And if we're going to the point where we're just setting it into motion, so we haven't started moving yet, we're talking about static friction. So we're talking about mu sub s. And if we're at the point where we're just getting it started, that means that we're talking about a situation. Remember, we said that this could be less than or equal to? Well, we're looking at the situation because it's when motion just begins where they're equal. So I've got my friction, my static friction force equals my coefficient of static friction times the normal force. Okay, so first of all, let's start off with this net force has to be 0. Let's start with the weight vector. F sub W, and this is going to be 24 times 9.81, which is going to give me negative 235 newtons. And I'm going to do each vector in a different color. All right, that means my normal force has to be, let's see, that's about that far. It's about that far, has to be equal and opposite. Okay, I have an applied force that's 75. So if this is 235, this applied force better be about, is that roughly about 75? Let's do, this guy got cut off. I got to adjust my camera. Well, remember, I'm not moving. I'm just at the point where I'm going to start moving. So my forces have to be balanced for this split second. So what does that mean for my friction force? What does the value have to be? Has to be negative 75 newtons. Well, the problem asks me for the coefficient of static friction. To do that, I have to have my normal force and I have to have my friction force. This is going to be negative 75. And by the way, coefficients are unitless and they're signless. So they're scalar. And this is going to be 235. So when I solve, I get a coefficient of static friction of 0.32. All right, I think we're only about 5 minutes in, so let's go ahead and do the second problem. I'm going to pause and recenter. Okay, so here we go. The next problem, a student moves a box of books by attaching a rope to the box and pulling with a force of 90 newtons at an angle of 30 degrees. The box of books has a mass of 20 kilograms and a coefficient of friction between the bottom of the box and the sidewalk is 0.5. Find the acceleration of the box. All right, so we have a box and it's on a surface, and I'm going to give myself plenty of space for my free body diagram. Okay, so what forces how many forces am I going to have here? Okay, if you said 4, you're correct. We've got friction, we've got an applied force, we've got a normal force, and we've got a weight vector. All right, let's start off with our weight vector. F sub W is going to be 20 times 9.81, and this is going to be negative because we're going to go with a traditional coordinate system. So when I multiply this, I get negative 196.2. And again, you'll notice I'm not doing vector banks. I'm not breaking them out into vectors. I like to kind of talk about the vectors as we go. I'm not going to put any other values on yet because I don't know how big those forces are, but I want to pick apart my problem a little bit. All right, first of all, find the acceleration of the box. Let's assume we're moving this direction, and I have width, that's W with acceleration. So that means that if I use some kind of F equals MA, this is going to have a number. This isn't going to be 0. We're not doing constant and we're not at rest. We've got coefficient of kinetic friction, and we've got mu sub K is equal to 0.5. Don't know quite how we're going to use that yet. All right, let's go ahead and put this 90 Newton vector on, because if this is a 196 vector, I know my 90 should be about, I'm going to give myself a horizontal, so this is going to be my horizontal axis, so I need about 30 degrees. And 90 is going to be about half that length, so that's more, that's like 45. Sorry about that. 90 Newton. Remember, this is going to have a horizontal component, and it's going to have a vertical component. Well, my motion is on the horizontal. So I now have two vertical vectors. I have FAY, this is FAX. I've got FW and FAY. If I don't have any vertical motion, what does that tell me about the normal force? Remember, so in my motion analysis here, F net Y is going to equal 0. F net X will equal the mass times acceleration. My motion's a horizontal, so it's my horizontal force that's going to result in acceleration. This, though, my box doesn't say my box is jumping up and down, is going to be 0. So that means that this plus my normal force has to equal 0. So if my vector is that long and I come up that far, I probably want to do about that. So now we see that Fn plus FAY minus FW equals 0. Those three vectors, both in my diagram and in my mathematics, have to end up meshing. It has to jive. Well, if this is my FAX, so what do I know about my net forces? So here is my net for the Y. So what about my net forces in, that's got to be net. What's going to make up my net forces in my horizontal? F net X is going to be my negative friction force plus FAX is going to equal my mass times my acceleration. And remember, force of friction is equal to mu sub K Fn. So when I look at this in totality, if I'm trying to solve for acceleration, I have mu sub k negative mu sub k Fn plus Fax equals ma. So let's start getting our pieces pulled in. Before we do that though, let's add our last vector. So I don't have my friction vector on here. If this is this portion, and I have acceleration this direction, what do I know about this vector that I'm going to draw? It has to be smaller. My friction vector has to be smaller than my horizontal portion of my applied force. This free body diagram is consistent with this. I have acceleration in the horizontal this way. I have no motion in the vertical. So you're beginning to see, hopefully, how important that motion analysis is. Well, we've got to put some numbers here. The only vector I have any values for is this 196. So let's split out FA, and I'll redraw. FA is 90 newtons. So this is FAX. This is FAY. I have 30 degrees, so this is going to be 90. And notice I'm back to cosine, positive 90, sine 30. And when I simplify, I get 78, and I get 45. Okay, so we said we were going to start pulling variables out. I'm solving for acceleration. My mass is 20. FAX is 78. Mu sub k is, so this whole term is negative 0.5. So I still need my normal force. Well, can I find that? I can, because I have this and I have this. Remember, my net y was 0, so F sub w is negative 196.2. FAY is positive 45. That gives me an Fn of 151 newtons, which is the last piece I need to bring in down here. When I do my algebra, I end up with, remembering this is negative, what do I get? What do I get? 0.125 meters per second squared. So we did some new things here, and let's highlight those new things that we did. So by having this vector on an angle, I had to consider my net forces in my y and my net forces in my x. I had to remember that my net and the y, down I had one piece, but up I had two pieces. I've got my normal force and I've got the vertical component of my applied force. I could still solve for my normal force. I had to remember that my net force in my horizontal is made up of two forces, the applied portion, the horizontal portion of the applied force, and my friction force. The horizontal applied force has to be larger than my friction force. That's going to give me my acceleration. I can take that friction force and I can expand that, mu sub k Fn. So we have what I call equation nesting. I'm nesting an equation inside an equation inside an equation. So we started off with one, we expanded it, and we expanded it again. So here was the initial, here is the second one, and then when I expanded it again, I ended up with number 3. This is a skill you're going to have to practice, and it's something you're going to have to become proficient in. Really, a lot of times on the AP test, you'll stop there. They'll say, come up with an equation to solve for acceleration. And that's it. That's your answer. They don't even care about the algebra. I find people are a little more comfortable if they can get to the end and they know they have a, this value, they got through the problem correctly. All right, so that is everything that we need for 5.05. Thanks for watching. Have a good day.